So for example number 4, I decided to copy the directions and do a problem from the homework assignment in which you are not given a grid to work with in terms of an x-axis that's already pre-labeled and then a y-axis that's pre-labeled. So here we have a problem that's asking us to find the amplitude, period, and phase shift, which we haven't discussed yet, of each function. Graph at least 2 periods, label key points. So a phase shift is a translation that is translation left and right. So it's shifting the trig function left and right. So that's what a phase shift is. And that occurs just like with my typical quadratic function. Let's say you had x minus 3 squared plus 4. If we see the negative 3 inside with the squared with the function, then we know this is right 3 versus this is up 4. So on my sine function that I have as an example, y equals 3 sine x minus pi. And I forgot to mention, feel free to hit pause to copy down the directions and the example. Once you have it copied down, I want you to pay attention to the fact that there is a amplitude we can tell is 3, which stretches the sine function. There's stuff going on inside the parentheses, which is going to affect the phase shift as well as the period. And then there's nothing being added or subtracted. So I'm going to go ahead and put plus 0. So no upward, up and down shifting or transformations. And then let's go ahead and graph this. So just like the previous problems, we're going to figure out amplitude, period, and then this time also add in the phase shift. Okay, so the amplitude is the value that you have in the absolute value of the a value in front of sine, the constant, which is 3. So it's going to be 3 high, 3 low. And then the period is equal to 2 pi divided by the constant that it's in front of x. So in this case, the constant that's in front of x is 3. So 2 pi over 3 is going to be my period, which remember, that means that roughly speaking, by the time you get to 2 pi over 3, that's what you should see. And then finally, the phase shift. So with the phase shift, we want to know if we're moving left, right. Please remember that when you're doing the phase shift, what needs to happen is the constant value that you see out front here, the 3, has to be factored from both 3x and pi before we determine any phase shift. So what I mean by that is we're going to rewrite the function with that constant value of 3 that affects my period factored out. So if I factor out 3 from those two terms, I get 3 times x is 3x. And then the question is, what would go here such that 3 times that value is equal to pi? So the simple answer is you take that value and then you divide by 3. Okay, so think through this. If I were to distribute, 3 times x is 3x. 3 times negative pi over 3 is negative pi. So this expression here is the same exact thing as the original. And so only then, after I've done that, is when I can determine the phase shift. So the phase shift is what's going on inside here. Okay, so what's being added or subtracted to x? In this case, negative pi over 3. So my phase shift would be right pi over 3. Remember that when we're looking at shifting functions left and right, it's always the opposite in sign of what you see inside the parentheses. So a negative is right. Okay, so the next thing is we're going to create a xy axis on our own. To me, this is a little bit easier. The hard part for many students is coming up with the values for the angle measures, which will be required of you guys to at least come up with the 4. So let's say we had, I think it's wise to go left and right 4. So you see how I equally parsed out the graph for spaces for 4 regions on the right and 4 regions on the left. Now I know right now that by the time I get to 2 pi over 3, I should complete one cycle, and same on the other end, negative 2 pi over 3, that would complete the other cycle. Okay, so what I do to figure out these angle measures right here is I take 2 pi over 3 and I cut it into fourths. So either divide by 4 or times by a fourth. And so that will tell me what I need to space my intervals apart as. So in this case, when you reduce, you get pi over 6. Okay, so 2 times 3 is 6. So pi over 6. So that means this first angle is pi over 6. This is going to be 2 pi over 6, which reduces to pi over 3. Then this is 3 pi over 6, which reduces to pi over 2. Then let's make sure this makes sense. This is 4 pi over 6, which reduces to 2 pi over 3. So that all works. The negative side is easy because we just make it the opposite in values to the angle measures on the right. And then from there, let's go ahead and we see that the amplitude is positive, so we're going to have a hill then a valley. So on my key points here, I know with the sine function it's hill then valley. So I'm going to start with the origin. I know in the middle it's going to come back to the x-axis, another x-intercept at 2 pi over 3. So same on the other side. Let's go ahead and fill out all our x-intercepts. Then in between the first 0 and pi over 3, we know we're going to hit a hill. The maximum is going to occur at pi over 6 and with a value of 3. So we're going to do our hill there. And then at pi over 2, we would have a minimum of negative 3. Then on the opposite end, if I were to, this is my pattern so far. Let me clean this up a little bit here. So we would have hill then valley. If I continued on the other side with that pattern, the minimum would be at negative pi over 6, the max would be at negative pi over 2. So we have here that the sine function would look like that. So now we're going to shift the whole entire graph right pi over 3. If you look at pi over 3, what represents a unit of pi over 3 is a space of 4 on the x-axis, or each one of those units that you see there is representative of a fourth of pi over 3 or a 12th, or pi over 12. So what we'll do is take each point and move it 4 units to the right, as in 4 of those boxes. So I'm going to draw my final graph in pink so that we can distinguish it from the initial graph. So initially you see that if you start with the point that is on the origin and you move it right pi over 3, that it doesn't appear the graph has shifted at all. But if we take the maximum at pi over 6 and move it right, we see that the maximum has shifted. And so the entire graph, if we now go ahead and move every single point right 4 spaces, we see that the entire graph has now shifted so that your final graph looks like a reflection of your initial graph. If I were doing this on the homework assignment, I'd probably not sketch my initial graph in green, just have the dots that represent the initial graph, and then go back through and draw your final graph in a solid color so it's a little bit easier to distinguish. On the homework assignment, I also will draw something that looks like that to say that is my final graph or after shifts. And then in my other color in green, I'd probably kind of like a key that you have to say that it's before.